after studying this module, you shall be able to understand the concept of hyperconjugation. Although you have learnt it earlier also, but we will learn it in more detail and go into in-depth study, know about the structural requirements in a molecule which are there to show hyperconjugation, learn about the important consequences and application of hyperconjugation, and you shall also be able to comprehend the concept of reverse hyperconjugation. So, let us begin with recalling that you have already studied about conjugation. In conjugation, you have studied in the previous module that the electrons, they move from one p orbital to the other, and the important condition which is required is these p orbitals should be aligned in parallel planes, so that the electrons can easily move from this to next p orbitals. So, now the question comes, is it possible for an electron to jump from a p orbital to sp3 orbital which are not parallelly aligned with one another? And the answer is yes. This type of conjugation is not normal, it is extraordinary, and hence the name you can say it is hyperconjugation. It is also called as no bond resonance or zero bond resonance, and let us try to study more about it. The normal electron releasing inductive effect, the plus I effect of alkyl groups, you are aware is in this order, that is CH3 is less, then ethyl is having a greater effect, then you have isopropyl and then the tertiary butyl group. But it was observed by Baker and Nathan that in conjugated systems, the attachment of alkyl groups reverse their capability of electron releasing. Rather, they suggested that alkyl groups are capable of releasing electrons by some process other than the inductive effect. When a carbon-hydrogen sigma bond is in conjugation, the sigma electrons of this bond enter into conjugation, and this is an extension of normal conjugation and was termed hyperconjugation. Unlike the normal conjugation wherein the pi electrons get delocalized in p orbitals, here sigma electrons move to pi orbitals and in turn become pi electrons. So, it involves the delocalization of CH sigma electrons to the p orbital. It essentially means that hyperconjugation depends on the presence of alpha hydrogen atoms. With the increase in number of such hydrogens, the electron releasing effect of the alkyl group also increases, and you can see now this is in a reverse manner, that is methyl will be more because it has 3 alpha hydrogen when it is positioned to a CC doubly bonded system or otherwise where is a p orbital, and this is greater than the ethyl because it has only 2 alpha hydrogens, followed by this isopropyl which has only 1 alpha hydrogen, and then followed by tertiary butyl which has no alpha hydrogen. The contributing structures involving the sigma electrons of CH bond do not show any covalent bond between carbon and hydrogen. Hyperconjugation therefore is also called as no bond resonance. It is important to note that hydrogen does not actually separate from the molecule, because if that happens, the necessary condition for resonance to occur will be violated. Hyperconjugation exists in the molecule having the following framework, that is either alkenes having CC double bond or the carbocations or the free radicals further joined to at least 1 alpha hydrogen atom, but not in the case of carbanions. So, you can see these are the 3 cases where you can observe hyperconjugation. And if you look at some examples, let us consider first the case of propene. You can see that this particular CH bond, if you consider, the electrons between this C and H can move to the adjacent CC bond, yet they are in the octet of this carbon, and at that very particular instance the pi electrons will be moving to the next carbon, giving rise to a minus charge on this terminal carbon, you can see, and between this C and H now there is no bond and rather H gets a positive charge. Similarly, the next hydrogen can participate and the next. So, these are the hyperconjugative structures of the propene. Taking another example, let us consider toluene, and toluene also you can see these are the 3 alpha hydrogens which can participate in hyperconjugation one by one. So, if we consider this particular CH bond, then it will lead to this structure where the carbon gets minus charge at ortho position to toluene and the H gets plus charge, and notice that between the C and H plus there is no bond now. So, it is the no bond resonance. The methyl group can be denoted as having plus H effect as it donates or gives electrons to the conjugated system. So, after knowing what is hyperconjugation and how to write the structure, let us look at what are the requirements for hyperconjugation. First of all, there must be an alpha CH group or a lone pair on the atom adjacent to sp2 hybrid carbon or other atoms like nitrogen, oxygen, etc. For example, alkenes, alkyl carbocations, alkyl free radicals, nitro compounds with alpha hydrogen. Due to the presence of hydrogen on the alpha carbon, which is next to the multiple bond, displacement of the sigma electrons towards the multiple bond takes place, which causes the polarization of the multiple bond. For example, in propene, the delocalization of sigma electrons of the CH bond of methyl group can occur into the p orbital of doubly bonded carbon, which is shown as here. You can see that this particular sigma bond, these 2 electrons will move to the p and further the p orbital electron move to the adjacent p orbital, giving rise to a minus charge on the carbon and positive charge on the H plus, and there is no bond between the C and H plus. Similarly, you can see that this can be represented like this, that where in place of 2 discrete p orbitals, it is the entire pi bond where there are 2 electrons, and that shifting has been represented as shown here. So, you can say hyperconjugation in propene is going this way, giving rise to C minus and H plus, where C and H plus there is no bond, and if the reverse happens, then you will be getting the original structure of propene. Likewise, remaining hydrogens on the methyl group also contribute in the hyperconjugation. It is possible because of free rotation of CC bond, so that other CH bonds can also contribute in the hyperconjugation. Therefore, propene molecule can be illustrated by the following resonance structures which suggest its stability. You can see that these no bonds resonance structures, they are shown by propene due to hyperconjugation, and because of this more delocalization, it is giving rise to the stability to the propene molecule. So, in these hyperconjugative structures, that is 1, 2, 3 and 4, the structure 2, 3 and 4 of propene, the bond between an alpha carbon and one of the hydrogen is absent, and this is the reason why we can call hyperconjugation to be also referred to as no bond resonance or zero bond resonance. These equivalent contributing structures, that is the second, third and fourth here, are also polar in nature, and hence they are responsible for the dipole moment of propene, which is 0.36 d. The bond length of Cc in propene is equal to 1.48. The range is 1.54 of the Cc single bond and 1.34 of Cc double bond, but due to the hyperconjugation, the approximate bond order of the Cc is 1.5, and this kind of hyperconjugation is also known as sacrificial hyperconjugation, as one bond is missing. Let us now look at the consequences and application of hyperconjugation. First of all, let us look at the stability of alkenes. As a general rule, greater the number of alkyl groups, that is containing the alpha hydrogen, attached on the double bond, greater is the stability of the alkene. And this is because there will be increase in the number of contributing no bond or the hyperconjugative structures which will be there. So, we can say out of 1 butene and 2 butene, 2 butene is more stable than the 1 butene. And if you look at the reason, you can clearly see that in case of 2 butene there are 6 alpha hydrogens which can be involved in hyperconjugation, whereas there are only 2 alpha hydrogens involved in hyperconjugation in the case of 1 butene. Hence, you can say the contributing structure in 2 butene are more as compared to 1 butene, and that is the reason why 2 butene is more stable than 1 butene. With the increase in number of methyl groups on the double bonds, the stability of alkenes will be further increasing, which is very obvious, and you can clearly look at this order and notice that ethene will be least stable, followed by when one hydrogen gets replaced by methyl, or when you have 2 then it will be even more stability. When you have 3 methyl groups on this ethene framework, then it will be even more stable, and when you have this tetramethyl ethylene, this will be more stable out of these. And this order has been justified on the basis of heat of hydrogenation data of the given alkenes. With the rise in stability of alkenes, the value of heat of hydrogenation decreases. For more substituted alkenes, the heat of formation is higher than expected. It must be kept in mind that the important condition for hyperconjugation to take place in alkenes is that the alkyl group attached to the double bond must have minimum 1 hydrogen atom. For example, in case of this particular alkene, as you can see here, which contains a tertiary butyl group on doubly bonded carbon, the hyperconjugation is not possible because there is no hydrogen atom on the alpha carbon. So, the effect of hyperconjugation is stronger than the inductive effect, and it is because in inductive effect there is only partial delocalization of charges, but in hyperconjugation there is a total transfer or delocalization of charge across these atoms. For example, considering the inductive effect, one may conclude that 1 butene is more stable than propene, as the positive inductive effect of ethyl group is stronger than that of the methyl group. But this is not correct. Propene is more stable than 1 butene, and this is due to the fact that there are 3 hydrogens on alpha methyl group involved in hyperconjugation, as you can notice here in case of propene. But in case of 1 butene, only 2 hydrogen atoms are there on this CH2 group that you can see, which can take part in the hyperconjugation. The next application we can see is the stability of carbocations. The ethyl carbocation is more stable than the methyl carbocation, and this is because the sigma electrons of the alpha CH bond in ethyl group are delocalized into the empty p orbital of the positive carbon center, and thus giving rise to no bond resonance structure, as you can see here. But hyperconjugation is not possible in the methyl carbocation, and hence out of the 2 the methyl carbocation is less stable. So, you can clearly see here how the hyperconjugation in ethyl carbonium ion or the ethyl carbocation is more stable because of the delocalization due to hyperconjugation. In general, as the number of alkyl groups containing these alpha hydrogens attached to the positively charged carbon increases, the stability of the carbonium ion increases because of increase in the number of contributing structures to hyperconjugation. And this kind of hyperconjugation can also be known as isovalent hyperconjugation, as there is no decrease in the number of bonds in the no bond resonance forms which are going to be formed. So, thus we can say the increasing order of stability of carbocations, you can see out of these will be as such: methyl will be least stable, followed by the primary carbocation, where you can notice that here there will be 3 alpha hydrogens which can take part in hyperconjugation. Then it will be this secondary isopropyl carbocation, and then the tertiary butyl carbocation will be more stable, because now there are 9 hyperconjugative structures which are possible. After this, let us look at the stability of free radicals. The stability of free radicals is influenced by hyperconjugation, very similar to as in the case of carbocations. One of the 2 sigma electrons of the alpha CH bond can be delocalized here into the p orbital of the carbon containing an odd electron, and due to hyperconjugation, the stability of free radical also follows the same order as that of the carbocation, that is methyl free radical will be least stable, followed by primary will be more stable, then secondary, and then the tertiary will be the most stable. Let us look at the application on dipole moment and bond length. The dipole moment of the molecules is greatly affected due to hyperconjugation, since the contributing structures, they show considerable polarity. The bond lengths are also altered due to the change in bond order during hyperconjugation. The single bond might develop partial double bond character and vice versa, as we have seen in the phenomena of hyperconjugation. For example, the experimental dipole moment of nitromethane is higher than the calculated value because of hyperconjugation. The experimental CN bond length is also less than the expected value because of the same region. So, you can see here the hyperconjugation in nitromethane is as shown here. The CH bond electrons, the sigma electrons will move to the CN, making the CN into double, and in turn the pi electrons between N and O, they get shifted to O, giving rise to O minus. The same explanation can be given to the decreasing CC bond adjacent to the cyano group in acetonitrile, and also the CC bond adjacent to the C triple bond C in propyne. Here also the observed dipole moments are different from their expected values, and the reason is because of hyperconjugation. And you can see here the acetonitrile hyperconjugative structure is as shown here, and similarly you can see the propyne hyperconjugation is leading to polarity as well as differential in the bond length. After dipole moment and bond length, let us look at reactivity and orientation of electrophilic substitution on benzene ring. In case of toluene, the reactivity of the ring towards electrophilic substitution increases, and the substitution is directed at ortho and para position to the methyl group, and this can be explained mainly by hyperconjugative effect. The methyl group releases electrons towards the benzene ring partly due to the inductive effect and mainly due to the hyperconjugation. And as you can see in these hyperconjugative structures in toluene, all these 3 hydrogens can take part one by one, and these are the no bond resonance or the hyperconjugative structures which can arise. And from these hyperconjugative structures, notice that the negative charge or the electron density on the benzene ring is being increased at ortho and para positions, and thereby these positions will be able to attract the electrophiles more than the meta positions will do. The inductive effect is comparatively weaker effect, and hyperconjugation will overpower it. So, as a result, in case of toluene, it becomes a ortho and para directing rather than meta directing as when the electrophile is attacking on them. And as a proof, consider the substitution, for example nitration on the disubstituted benzene, which occurs ortho to the methyl group and not ortho to the tertiary butyl group. And this is because although tertiary butyl group has a greater inductive effect than the methyl group, the tertiary butyl group, because there are no alpha hydrogen in it, cannot exhibit hyperconjugation. So, you can clearly see in this particular case that nitration will happen ortho to methyl and not ortho to the tertiary butyl group. So, this is clearly a proof of the existence of hyperconjugation. Further, also note that the tertiary butyl group is bulky and will be hindering the approach of the electrophile. Then let us move to the application on anomeric effect. The overall tendency of anomeric substituents to favor an axial position is what is called as anomeric effect. For example, the alpha methyl glucoside is more stable than the beta methyl glucoside, and this can be exhibited or explained due to the hyperconjugation. The non-bonding HOMO with a pair of electrons on the ring of alpha methyl glucoside oxygen is anti-periplanar to the anti-bonding lowest unoccupied molecular orbital of CO bond in methoxy group, and this anti-periplanar arrangement of orbitals allows the hyperconjugation between them, which will be stabilizing the alpha form, and this type of stability is not possible in the beta form. So, you can notice this structure that this HOMO is interacting with this LUMO, and this is because of the anti-periplanar arrangement and leading to the stability of the alpha form. So, whereas in the beta glucoside the methoxy group is at equatorial position, and that cannot be involved in hyperconjugation since it is not anti-periplanar to the lone pair of the ring oxygen. Therefore, beta methyl glucoside is less stable than the alpha methyl glucoside. After this, let us look at one more term, which is reverse hyperconjugation. For alpha haloalkenes, the delocalization of electron takes place not away but towards the halogen group through hyperconjugative mechanism, and this is because of the electron withdrawing nature of halogens, and this is then known as the reverse hyperconjugation. The dipole moments of the alpha haloalkenes hence are remarkably increased because of this phenomena, as you can see the case of this allyl chloride. The CCl bond, these sigma electrons will move towards the Cl, giving rise to Cl minus and a no bond between C and Cl, and in turn this carbon electron deficiency will withdraw the pi electrons from the adjacent CC pi bond, and we get this particular terminal carbon getting a plus charge. So, this is also hyperconjugative structure, but it is happening in the reverse direction, and it is called as the reverse hyperconjugation. So, dear students, let us now summarize what we have learnt in this module. We have studied about hyperconjugation in this module, and we studied the delocalization of sigma electrons or lone pair of electrons into the adjacent pi orbitals or p orbital is called as hyperconjugation. We also studied that it takes place because of overlapping of sigma bonding orbital or the orbital containing a lone pair with an adjacent unfilled p orbital, and it is also called as no bond resonance or zero bond resonance, and also as Baker-Nathan effect. It explains the stability of alkenes, carbocations and free radicals among with various other parameters like dipole moment, the change in bond length, bond order and so on. We also studied at how hyperconjugation explains the reactivity and orientation of electrophilic substitution on alkyl substituted benzene ring, and how the anomeric effect that the alpha methyl glucoside is more stable than the beta methyl glucoside due to hyperconjugation. We also studied the reverse hyperconjugation and considered the case of alpha haloalkenes, where the delocalization of electrons takes place towards the halogen group through hyperconjugative mechanism, which is because of the electron withdrawing nature of the halogen.